Welcome to Value Gene Insight Conversations.
We're jumping straight into a really critical strategic discussion today.
Yes, we are.
Our focus is on the monumental shift happening in industrial automation. Specifically, how humanoid robots are moving, and moving rapidly, from the realm of speculative research
Right.
directly into the operational heart of the manufacturing sector, and especially within food and beverage processing.
And that's the core of the dilemma we consistently see with our clients. I mean, we spend so much time talking about technology investment, but there's this pervasive, almost chronic issue.
Stagnation.
Exactly. Efficiency gains in many food factories they have largely stagnated over the last decade. And this is despite massive capital injections into world-class equipment and advanced tech. Capacity is still lost every single day. It just bleeds out in these small accumulated operational struggles, the minor jams, the slight variances, cleanup delays.
Exactly. The bottleneck isn't the big, shiny machine itself.
Yeah.
It's that fragile execution layer.
And that fragility is being amplified.
Dramatically.
Mm-hmm.
It's being intensified by a structural labor crisis. And we have to be really clear here. This is far beyond a temporary post-pandemic hiring problem.
It's just systemic.
It is systemic. It's a long-term talent deficit in U.S. manufacturing. I mean, if we just look at the data, as of early 2024, the broader manufacturing sector was already burdened with roughly 622,000 open jobs.
Jobs that companies just couldn't fill.
Could not fill.
And the future projections we're tracking, they're genuinely sobering for anyone who's managing long-term capacity.
They are.
By 2033, the sector might need 3.8 million new workers. That's for replacing retirees and just supporting growth. But nearly half of those positions, an estimated 1.9 million, could very likely go unfilled.
And that creates a hard capacity ceiling. It's a ceiling that no amount of traditional fixed automation can solve, because you still need people. You need people to operate, to maintain, and to manage all that complexity.
And we really have to emphasize that this shortage disproportionately hits food and beverage processing.
It does. This subsector faces one of the highest average turnover rates in all of manufacturing. We're talking 28 to 36% annually.
So why is that? Why so high in food and bev?
It's the nature of the work.
Okay.
The mixing, the lifting, the sanitation, the tight adherence to these very repetitive processes. It's physically demanding. It's often in cold or hot environments, and it requires immense focus for what is, at the end of the day, low-complexity work.
So retention is just a constant drain, organizationally and financially.
A huge drain.
And this is precisely where the emerging humanoid value proposition becomes so compelling. When we talk about humanoids, we're defining them as human-grade robots.
Right.
They're fundamentally designed to offer a new, resilient model of labor capacity. They aren't niche tools. They're general-purpose assets that are capable of performing the full spectrum of human-equivalent tasks.
And this is the key point.
Using existing factory layouts and tools.
We view them as the key to a fundamental transition for the industry. It's about moving away from a volatile, labor-dependent operational model toward one that's defined by asset-based resilience.
So our mission in this deep dive is really to provide you, the decision maker, with a clear, objective assessment.
Yes, we're going to dissect the readiness timelines, the economic viability, the operational vision, and the strategic steps required to successfully integrate this emerging technology into your long-term capital and operational planning.
We really believe you have to prepare for this future now.
You do.
Okay, that sets the stage perfectly. Let's move into the technical core of the discussion. We'll call this section Modern Humanoids, Capabilities, and Development Trajectory.
Good.
So the promise, as you mentioned, is that these are being built as general-purpose automation platforms, and they're designed specifically for the, quote, human environment. They should, theoretically, be able to navigate our clients' existing facilities, the doorways, the tight aisles, standard equipment, without us having to spend hundreds of millions on a complete factory redesign.
And that versatility, that ability to use existing infrastructure, that's the disruptive factor.
Right.
However, for these platforms to move from exciting prototypes into scaled industrial assets, they have to overcome enormous engineering hurdles. And they have to meet very strict industrial expectations.
So how have we structured that assessment?
We've structured our readiness assessment around 4 core engineering challenges that really define near-term viability. They have to be productive, accurate, fast, safe, durable, compact, and above all, they must be economically viable.
Okay, let's unpack these 4 challenges, starting with the first one. And this is arguably the most immediate constraint. Energy efficiency, we're calling it the the duty cycle challenge?
It's simple physics, really.
Yeah.
Unlike a fixed machine that's bolted to the floor, humanoids have to carry their energy source with them while they're walking, balancing, manipulating things.
And food manufacturers need long duty cycles. They need something that fits their operational rhythms, allowing for predictable 4 to 5 hour scheduling across continuous shifts.
And this challenge is forcing manufacturers to innovate
Yeah.
and to do it aggressively. We're seeing two primary workable operating models emerge in the current industrial pilots.
Okay. What's the first one?
The first, which you see with companies like Apptronic and their Apollo robot, targets extended multi-hour runtime. And it emphasizes hot swappable batteries.
So the focus there is on maximizing uptime.
Exactly. Maximizing operational availability by minimizing the time you need for energy replenishment. Just swap and go.
And the second model?
The second approach, which we see with Agility's Digit, leans more into what we call a charging ratio model.
So they accept a shorter runtime?
They might, yes,
Yeah.
say 90 minutes to 2 hours.
Yeah.
But they pair it with extremely rapid, high-cadence recharge cycles. In a very structured, low-travel factory environment, this ratio can still yield excellent operational availability.
But the crucial point here for both models is that energy planning and managing that duty cycle volatility are core deployment considerations right now. I'm just struck by the physics problem here. When we look at extending useful runtime, the trade-offs are intense. I mean, increasing the battery mass seems like the obvious lever to pull, right?
It does, but it creates a steep, nonlinear penalty.
How so?
Well, a heavier robot needs exponentially more power for just basic movements like walking and balancing. This then demands larger, heavier actuators, more complex cooling systems.
Which only compounds the initial weight problem.
You get into a vicious cycle of mass and power consumption.
That's why we believe the most immediate and frankly faster gains will come from reducing the internal power draw through system efficiency, rather than just waiting for some battery revolution.
You'll give an example.
Sure. Look at a current generation model like Tesla's Optimus. It uses a 2.3 kilowatt-hour pack at a conservative average power draw of 1 kilowatt, which is pretty typical for a demanding, continuous task that only gives you about 2.3 hours of operation.
Which is just not commercially viable for a 2 or 3 shift operation in a food facility.
Precisely. So to solve this, the near-term engineering efforts are all focused on what we call energy metabolism.
So optimizing actuators.
Optimizing actuator efficiencies, refining smarter motion planning algorithms to reduce wasted energy during movement, and designing better thermal paths to keep components running optimally.
These are the improvements that provide quicker incremental gains rather than just waiting for a chemical breakthrough.
But those chemical breakthroughs are still absolutely vital for achieving, shift parity, especially for the labor arbitrage case.
Right.
Today's lithium-ion batteries are excellent. They're hitting energy densities of roughly 200 to 260 watt-hours per kilogram. But if a humanoid battery pack weighs around 12 kilograms, that mass-to-energy ratio fundamentally limits the runtime.
So to hit that strategic target that food manufacturers need, that 5 hours of continuous heavy-duty operation, what's the number?
We need pack density to approximately double. We need to reach around 420 watt-hours per kilogram or more.
And the industry roadmaps do provide some hope, but they require patience. We're projecting system-level energy densities approaching 350 watt-hours per kilogram by around 2035.
And that would support maybe 4 hours of heavy-duty work with that same 12-kilogram pack? That's a major commercial milestone.
It is. However, the real game changer lies in the maturation of solid-state batteries.
What's the optimistic scenario there?
In an optimistic yet targeted scenario, reaching 600 watt-hours per kilogram by 2035. That could enable that same 12-kilogram pack to deliver approximately 7 hours of continuous operation under demanding workloads.
And that 7-hour window, that fundamentally changes the entire shift dynamic.
It does, which leads us directly to the second engineering challenge. And it's intimately related to power consumption, continuous operation.
Right. This is the ability to sustain productive work for those 4 to 5 hours required by the industrial rhythm, with operational availability consistently exceeding 85%.
And you noted that today's humanoids don't meet this standard yet. And the core culprit is heat.
That's the toughest lock to crack in the short term. To be strong enough to lift, say, an ingredient sack or move heavy trays, while still being agile and relatively light, humanoids rely on high torque density actuators.
These are motors that pack immense power into a very small volume.
But with current actuator efficiencies, sustained high torque leads to rapid heat buildup.
And when that internal temperature gets near the safe operating limits, The robot has to initiate thermal throttling.
It slows down.
It slows down, it reduces torque, or it just stops entirely to cool off. This involuntary pause is what prevents reliable, all-day industrial operation.
So the solution can't just be one single breakthrough. It has to be a layered stack of advancements. We've seen this in other complex systems, like jet engines, where performance improvements come from many small steps.
Right.
So what are the three layers you see addressing this thermal challenge?
First, it's incremental, step-by-step gains in the actuator efficiency itself. We've seen similar gradual improvements in other electromechanical systems.
But even small gains add up over time.
They do. Even modest gains of 2 to 7% annually in efficiency could translate into 1.2 to 2 times longer continuous work windows over a 10-year horizon. This is physics optimization refining windings, magnetics, gearing.
And the second layer.
Active cooling. This is it's non-negotiable for high cadence work. Approaches like liquid cooling and advanced heat spreading designs, which are already standard in high-performance computing, they have to be miniaturized and ruggedized for the robot's joints.
But there's a trade-off there.
A clear one. Added complexity, added weight, and potentially increased difficulty with the washdown and sanitation protocols that are so common in food processing environments.
And finally, materials science.
Yes, utilizing alternative materials that either tolerate higher temperatures or just move heat away more effectively. And this materials discovery process is being increasingly accelerated by AI-supported computational simulation.
Which allows designers to move beyond traditional copper and steel much faster than ever before. Okay, moving to the third critical domain. Onboard decision-making, or what we call fast and safe autonomy. In an industrial setting, a robot simply cannot rely on a cloud connection for real-time actions. Things like balancing itself when a floor is slick, or gripping a fragile product, or stopping a collision.
Milliseconds matter.
They literally determine safety and yield.
Absolutely. Industrial humanoids require a robust, self-contained, local decision loop. We call it edge compute.
The local brain.
It is. It's the local brain that handles moment-to-moment perception and control, independent of any cloud connection latency. The cloud is still vital for large-scale model training and fleet learning, but the factory floor requires real-time independence.
But the massive constraint here is that the powerful compute required for that draws significant power and generates substantial heat.
Which ties back directly to the two previous challenges we just discussed.
Exactly. So to run high-resolution sensor streams, multiple cameras, LiDAR, tactile sensors, and process all that simultaneous decision logic for balance and pathfinding and manipulation at factory speeds, the compute capability needs to increase dramatically. Our analysis suggests a required leap of about 25 to 50 times relative to today's advanced chips. We project this raw performance level will be technically available within the next 5 years.
Okay, so that's the performance timeline. But sustained industrial operation depends on efficiency.
Right. To keep that power draw manageable and avoid thermal throttling, compute efficiency and heat management need to improve by approximately 20 to 30 times over the next 6 to 8 years.
And if we don't hit that efficiency target?
We simply cannot perform sustained high-cadence work because the robot will, for lack of a better term, cook itself.
And we can't overlook the plumbing here either. Faster processors are useless if they're starving for input data.
Right. To feed these increasingly richer multimodal models and sensor streams efficiently, memory bandwidth might need to increase by around 4 times. That's to reduce the bottleneck between the sensors, the memory, and the processor.
So it's an integration challenge as much as it is a raw silicon challenge.
It is, and that brings us to the fourth and final domain, dexterity and precision.
This is perhaps the most challenging one for food manufacturing, especially when you're handling variable, fragile, or deformable items, think soft dough, delicate pastries, or irregular produce packaging.
Human dexterity, that ability to feel and react. It remains significantly beyond current robotics. It's a problem of mechanical and sensory complexity.
Let's break down the limitations here. The first one we see is a fundamental mechanical challenge, high degree of freedom hands.
So hands with lots of moving parts like a human hand?
Exactly. They're essential for fine manipulation, but integrating compact motors into each finger massively complicates heat dissipation and power consumption. Again, you're forcing those trade-offs with sustained performance. You can't just scale down a large motor and expect the heat to vanish.
Second is the sensory gap. Tactile sensing.
The sense of touch.
Right. While we have developed multi-finger designs that can detect low forces, the coverage, The number of sensor points and the data bandwidth of the feedback still lag significantly,
So current systems have to rely heavily on high-resolution vision.
which is ineffective when you're gripping an opaque object that might slip, or when you need that nuanced in-hand reorientation that requires physical feedback.
And finally, control efficiency.
Right.
Even with good mechanics and sensors, processing that high-dimensional tactile data and multiple inputs requires powerful onboard compute and highly efficient learning models. We need far better generalization in these control models to reduce the reliance on human guidance and ensure consistent performance across product variability.
Which is the nature of food.
It is. So when we look at the overall maturity roadmap, the process is layered.
The 2026 to 2030 window, that's focused on stability and initial industrial work. We're talking system-level efficiency, practical heat management, and good enough on-robot compute for controlled settings, like warehousing.
Then the 2030 to 2035 period is the major shift. It's the shift to long duty cycles, driven by better battery packs, active cooling becoming more common, and dexterity moving toward what we'd call industrial adequacy for structured tasks.
And finally, 2035 to 2040 focuses on deep industrialization, high thermal tolerance, robustness, and critically cost-effective, serviceable dexterity at true scale.
So the message we should take to our clients is that the technology is marching forward, but it's a layered, complex stack of challenges where every single solution introduces a new trade-off.
Usually related to heat or power.
Usually. But the technology's trajectory is undeniable. Which brings us neatly to our next section. If the technology is this complex, the ROI has to be crystal clear. We need to analyze the economics of humanoids in food manufacturing.
Right. We've established a nominal 10-year horizon for deep industrialization, hitting that 2035 to 2040 window for advanced autonomy.
But for executive decision-making today, this strategic question is whether external factors are accelerating this timeline. Is current investment defensible?
And we believe the answer is a firm yes. Our analysis shows that we could potentially pull broad adoption for scalable, structured use cases forward to around 6 years.
Making 2030 the critical inflection point for many food manufacturers.
Exactly. And this isn't just optimism, it's an objective analysis of external market and technological dynamics that are fundamentally reshaping the robotics commercialization curve.
And that acceleration is dependent on three forces strengthening simultaneously. The first is capital intensity and strategic validation.
Explain that.
The structural labor constraints are now so acute that humanoids are being viewed less as R&D and more as essential capacity insurance.
When the U.S. economy signals roughly 7.7 million job openings, the investment in automation is justified, even at early price points, because capacity has become the limiting factor for growth.
And we are seeing massive capital inflow reinforce this, which compresses the iteration cycles. Figure AI, for example, is reported to have secured massive commitments at a reported $39 billion valuation.
Right. And VC investment across the sector is rising sharply, potentially tripling in 2025 to $5 billion.
This inflow funds not just research, but the scaling of manufacturing. It pulls scarce engineering talent into the ecosystem, and it accelerates the entire commercialization pipeline much faster than the linear historical curves of traditional automation.
But I want to inject a critical counterpoint here, because executives will inevitably ask, what if this is an AI bubble? What if figure AI's valuation is speculative? The timeline might accelerate, but the risk remains high if that capital is deployed inefficiently.
And that's a fair question. Our analysis shows that the acceleration is defensible because of the second force. AI is compressing the R&D cycle time.
That is the real differentiator. AI is shortening development cycles by reducing the reliance on slow, expensive, physical prototyping. We see systems like Google DeepMind's Alpha chip producing competitive chip floor plans in hours, a task that traditionally took human engineers weeks or even months.
So when component design accelerates, the overall humanoid roadmap moves faster.
And here's where it gets really interesting for food manufacturers deploying small fleets. Fleet learning.
This allows robots to improve as a coordinated system, not just as isolated units.
So if one robot on a primary packaging line figures out a more efficient way to pick a slightly irregular product,
That optimal behavior can be validated in centralized simulation and instantly distributed across the entire fleet through an over-the-air software update.
this shifts learning from slow, individual physical repetition on the factory floor to centralized compute. It accelerates the arrival of human-level task capability far sooner than we would have expected.
So we're not waiting for 1,000 iterations of hardware. We're waiting for software to iterate a million times in the cloud and then deploy the solution instantly.
Exactly. That explains a rapid curve. What about the third force?
The third factor is leveraging mature tech. Humanoids are not starting from scratch. They are standing on the shoulders of high-volume adjacent industries.
Like EVs.
The massive scale of the EV and consumer electronics booms drove huge cost declines and performance gains in core components like batteries and power electronics. We've seen inverter efficiency, critical for robot motors, move from 90% to over 97% in a relatively short period.
And that efficiency gain immediately feeds back into our duty cycle challenge, right? Less waste heat, longer runtime.
Exactly. Similarly, the industrial automation sector itself has provided critical step change gains. Industrial servo motors has already delivered 2 to 3 times gains in torque density since the early 2000s.
Giving humanoid designers lighter, stronger, and more thermally stable components to start with.
And the drone industry's scale has reduced the cost and improved the robustness of critical sensors like IMUs and cameras. Humanoids are inheriting mature, scaled, and cost-optimized supply chains.
Okay, given that context of acceleration, let's turn to the numbers. Let's discuss total cost of ownership and ROI.
The core financial forcing function is simple: scale. We need to move production from the prototype phase through early mass and toward the mature phase.
And today's prototype CapEx anchors at what, $160,000 or more per unit?
At least. And while the bill of materials might be around $90,000, a significant 30 to 40% of that total cost is locked in the non-material integration layer.
Bespoke software, proprietary compute overhead.
R&D costs spread over very low volumes. That high initial price point is a huge barrier to adoption.
So the strategic goal must be rapid cost compression. In the mature phase, driven by the high volume adoption we project, CapEx is estimated to compress dramatically to around $50,000 per unit. How do we get there?
2 primary drivers. First, a 70% drop in actuator and structural costs. This happens when that bespoke machining shifts to automotive volume casting, dramatically reducing manufacturing complexity and time.
And second,
A 50 to 75% drop in compute costs. This is facilitated by the shift from expensive general-purpose GPUs used in the R&D phase to custom cost-optimized ASICs, designed purely for the inference tasks needed in the field.
okay, now let's consider the annual operating burden, or OpEx. Even in the early mass phase, where we anticipate first commercial scale deployments, say, at an $80,000 per unit, CapEx annual OpEx is estimated between $15,000 and $30,000.
And we must stress that electricity is a non-factor here. It's typically less than $1,000 annually due to the efficiency of modern humanoids.
The real cost lies in 3 structural buckets.
First is maintenance. We model this at 10 to 15% of CapEx annually, so roughly $6,000 to $12,000. This covers crucial preventative joint swaps, component degradation, and consumables like replacement grippers and sensors.
Things necessary for a high cadence, sometimes harsh industrial environment like food production.
Absolutely. The second bucket is the oversight premium. This is the key friction point we need to manage.
Early mass humanoids, lacking the sheer tenure and experience of their human counterparts, will inevitably fail gracefully or encounter edge cases they can't resolve.
Which necessitates a substantial 1 to 5 or 1 to 10 human supervision ratio. We have to factor in the cost of highly trained engineers or supervisors managing these assets.
And third is software and skill acquisition. Humanoids require continuous cognitive support.
So we're forecasting recurring subscription fees for over-the-air training modules that expand the robot's task library. For instance, teaching the entire fleet a new complex sanitation protocol.
And we also anticipate usage-based fees for complex cloud inference when the robot encounters a high-level anomaly that requires off-board processing capacity.
Okay, so let's test that TCO figure. If we amortize the $80,000 early mass CapEx over an 8-year lifespan, we get $10,000 to $16,000 in annual capital cost.
And when you combine that with the high-end OpEx,
The fully burdened cost of a human-grade unit settles at $25,000 to $46,000 per year.
yes, that is the calculated TCO. But I want to go back to your point about supervision. If we assume a high-end supervisory salary of, say, $120,000 annually, and we assign 5 robots to 1 supervisor,
That adds $24,000 per robot just for oversight.
which pushes our high-end TCO from $46,000 closer to $70,000 in the very early days, this is a critical risk factor.
But it's a temporary one. As that fleet learning matures, that supervision ratio rapidly drops, maybe to 1 to 20 or 1 to 50 within a few years, bringing the TCO back down aggressively.
Which makes the investment case clearer. It's a strategic transition from volatile OpEx, the rising cost and inconsistency of human labor, to predictable CapEx.
Even if the earliest TCO hovers around $60,000 to $70,000, it still represents a defensible strategic move against the volatility of a fully burdened U.S. food worker.
Which costs $80,000 or more annually when you factor in wages, benefits, retention costs, and inherent turnover disruption.
And the ROI is accelerated by what we call the labor multiplier.
Explain that.
Because a humanoid unit maintains a continuous high-cadence output, eliminating breaks, fatigue, and shift change deceleration. A single unit can effectively displace 1.5 to 2.2 human equivalents over a standard two-shift operation.
So even with high early costs, this labor arbitrage sustains an 18 to 22-month payback.
And in the mature phase, when that $50,000 CapEx is paired with low oversight, the payback accelerates dramatically to 7 to 10 months.
Let's make this tangible with our illustrative bake company case study. Imagine a typical $100 million annual revenue commercial bakery high variability, currently running at a low 65% overall equipment effectiveness, and burdened with 12% raw material waste.
The first most immediate value shift is in material yield and waste reclamation.
Right. Raw ingredients are the largest cost, consuming about 50% of revenue, or $50 million. Their current 12% waste translates to $6 million in lost product.
So by deploying humanoids that maintain precise control over mixing, portioning, and handling, we can eliminate spillage and variance. This transitions the company to a 5% unavoidable steady state.
Which effectively reclaims $3.5 million in annual gross profit. That money goes straight to the bottom line without selling a single extra cookie.
Second, OEE optimization. That 65% OEE is what we call a symptom of human friction. Lost time during shift changes, equipment staging lags, performance losses due to fatigue, or manual intervention.
So neutralizing those human variables transitions the company to an 80% OEE steady state. That 15 percentage point surge not only achieves baseline volume faster, but it creates 20% additional capacity.
And for a growth-constrained company, that capacity expansion is revenue that was previously locked away.
And third, the direct headcount calculus. If this bake company spends $10 million annually on 110 employees for 2 shifts, the humanoid shift multiplier 1 robot covering 2 human shifts, and the unit's continuous 95 to 99% efficiency shrinks the necessary labor footprint significantly.
Labor OpEx can potentially drop from $10 million to a projected $2 to $3 million over the transformation period.
So the cumulative financial impact is truly transformative. We're talking $3.5 million in yield reclamation, $7 to $8 million in direct labor arbitrage, plus the significant revenue potential from expanded capacity.
The total annual value shift is nearly $17 million. This moves the bake company from being a 5% net margin laggard in the sector to a 20+% margin leader.
And achieving full capital recovery within 9 to 12 months. The economics frame the humanoid not as localized automation, but as a complete recalibration of the manufacturing cost curve.
Let's transition now from the spreadsheet to the shop floor. We need to help our clients envision a fully humanoid-run food factory, a large-scale industrial bakery perhaps 10 years in the future, to understand the high-impact operational implications of this shift.
This vision begins with continuous 247 operations. Humanoids managing every single step, from inbound ingredient handling, unloading, transporting, dispensing 50-pound sacks, to complex mixing and outbound boxing. They're tireless.
And critically, these robots operate continuously. They require only 5-minute breaks to change their batteries, which dramatically boosts throughput and reduces per-unit costs by eliminating fatigue and shift change slowdowns.
The primary operational consequence is just the absence of volatile downtime. The ovens and production lines run constantly. The robot's productivity remains consistently high across all hours.
Which is simply unattainable with human crews alone.
But the real value isn't just in relentless speed, it's in quality and consistency at machine speed. Humanoid robots follow recipes exactly, dispensing ingredients with gram accuracy. Their integrated AI and sensor systems enable sophisticated, rapid quality checks using high-resolution optical, thermal, and potentially chemical sensors built right into the end effectors.
Consider the real-time feedback loop. A batch of baked goods exits the oven. The on-robot AI can detect a slight deviation in color or texture indicating an overcooked batch and automatically adjust the oven temperature and ingredient ratios for the next run within seconds.
So this rapid feedback ensures uniform quality with 10 times the efficiency and 5 times the precision of human inspectors. This meticulous control nearly eliminates the product variance and spillage common with manual handling.
And this shift also massively enhances safety. Every food processing environment has injury-prone tasks, moving heavy, hot trays, lifting heavy ingredient bags, repetitive motions that cause strain, or cleaning dangerous hot equipment.
These tasks are handled entirely by robots, eliminating significant risks, regulatory exposure, and workplace injuries.
Now let's look at resilience. Self-organizing operations. In a conventional factory, if a critical piece of equipment fails, say a mixer motor jams, the entire line halts while workers scramble to diagnose the issue.
Right.
In the humanoid factory, robots are equipped with deep, self-organizing intelligence. They constantly monitor equipment and each other.
So the moment an anomaly is detected, maybe a conveyor belt begins running rough or a temperature sensor spikes, nearby humanoids pivot and reallocate resources.
Yes. One pauses the line, others reroute the dough or mixture to alternate equipment using secondary paths. A designated maintenance humanoid fetches a tool from a nearby cabinet and performs a jam clearance or a component swap.
The system effectively self-heals the production process, minimizing downtime to seconds or minutes.
And crucially, every incident, every diagnosis, and every resolution is instantly uploaded to the centralized cloud AI system for fleet learning.
So the next time a similar issue occurs at any plant in the fleet, the robots resolve it even more efficiently, having refined their diagnostic and corrective approach.
This high level of resilience handles the daily disturbances that normally lead to OEE erosion.
So what's the evolving human role in this high autonomy environment? It shifts entirely from manual labor to supervisory and expert functions.
A single human operator might oversee multiple, fully automated plants from a centralized control center, intervening only for high-level, truly novel problems, perhaps via teleoperation.
So the factory floor itself may run for days without any humans present, save for periodic safety checks.
And humans are still responsible for the highest level tasks: strategic decisions, system design, creative product development, and complex regulatory maintenance audits. The expertise required is higher level focused on governing the system, ensuring quality and compliance, and interpreting data, not executing the repetitive labor.
The shop floor becomes predictable, managed through data, rules, and a small number of highly skilled human interventions.
That autonomous vision is compelling, but it confirms that the transition will not happen all at once. It unfolds in predictable stages, which we categorize as the humanoid transformation waves in food manufacturing.
We need to advise our clients that adoption follows a necessary adoption ladder. You move systematically from work that is structured, standardized, and low exception, the low-hanging fruit, to work that is increasingly hygiene-constrained, dexterity-heavy, or judgment-laden.
Table 1 in our analysis frameworks this progression by activity cluster and timeline.
Let's detail those categories, focusing on specific food applications. The early wins, 2026-2030, are driven by processes that are already measurable and have constrained variability.
This includes inbound handling, basic, moving standard totes and cases from the dock to staging areas, secondary packaging, handling rigid boxes or easier to standardize containers, and basic warehouse operations, like put away and replenishment.
The commercial logic is strong here because the work is repetitive and performance is easily quantifiable.
But there's a critical strategic implication, as we noted earlier. Plants that already run a clean, audited inbound logistics process will adopt faster. The robot inherits order rather than chaos. Operational discipline is the critical prerequisite for Wave 1 success.
Okay, moving to the midterm scaling, 2030-2035, we encounter activities requiring more robust handling and deeper integration with digital governance systems.
This includes inbound handling, advanced dealing with large, irregular sacks of ingredients, managing dust, navigating damaged pallets. It also includes primary packaging, where the product is fragile, often deformable, and stringent food-safe handling is essential.
And this is where physical execution meets the digital ledger. Batching and charging.
Humanoids become viable in this critical high-value step only when they can dose through structured interfaces and generate audit-grade evidence of exactly what was added, when, and how much.
So the real gating factor for many midterm activities isn't the robot's arm strength, but the integration with digital systems, recipe governance, traceability, and planning.
If the MES is messy, the robot can't perform audit-grade work. It's that simple.
Then the advanced autonomy 2035-2040 phase is reserved for work that requires high trust, complexity, and human-like judgment.
This cluster includes advanced cleaning, so deep cleaning, allergen washes, intricate component disassembly. It also includes advanced maintenance reactive diagnosis, identifying and solving truly novel problems, and new product testing, where judgment under uncertainty is required.
The threshold here is absolute trust. The cost of error in a sanitation breach or a faulty quality release decision is catastrophic for a food manufacturer.
Advanced sanitation provides a perfect example. It requires combining safe tool use in wet, chemical environments and reliable step-by-step execution without missing a single surface. The robot has to prove its ability to follow strict procedures, and the system must support verification, like automated swab results, before production can safely restart.
That trust takes time to accumulate.
It does. And this phased readiness naturally leads to the three transformation waves of deployment. The transition is not a single technology adoption, it's an organizational evolution.
So wave one is pilots in structured, low-exception work. The focus here is on introducing a small number of humanoids in tightly bound tasks, like dock moves or simple line-side material staging.
And the operational mode is defined by human-robot collaboration as the default. Humans manage the pace, set up the task, handle exceptions.
While the robots execute the narrow, repetitive moves under frequent human oversight.
And the goal of Wave 1 is confidence building, demonstrating reliability, stable operation over hours, and safe behavior around human workers, all of which is necessary to justify broader scope and capital commitment.
Then wave two is scale up across lines. Humanoids stop being an R&D curiosity and become part of the operating system, scaling structured domains across multiple shifts and multiple lines, warehousing, secondary packaging, simpler equipment interventions.
This wave serves as a strong operating model forcing function. If material locations are ambiguous, if standard operating procedures are ignored, or if changeover discipline varies by shift, robot performance immediately becomes unreliable.
So wave two mandates that plants standardize processes, interfaces, governance, and data integrity. They have to clarify buffer zones and unify material locations so robots can operate reliably without constant human escort. The plant's ceiling for automation is set by its own pre-existing process clarity.
And finally, Wave 3 is full-scale humanoid operations. This is where humanoids tackle the factory's hardest, most high-stakes work: high-care sanitation, complex reactive maintenance, and advanced quality decisions.
Operationally, the human role shifts almost entirely from doing to governing and intervening. The shop floor becomes predictable, managed entirely through data and rules, with a small number of highly skilled human interventions.
And critically, Wave 3 rewards the plants that use Waves 1 and 2 to standardize their processes. They will translate advanced humanoid capability into maximum commercial outcomes: lower scrap, higher uptime, higher resilience, while those who waited will struggle with amplified organizational friction and costly retrofits.
So our deployment strategy recommendation is clear. Most plants should start function by function. Concentrate learning and value in areas like warehousing or secondary packaging before attempting line-level transformation as complexity is mastered.
It's about building that organizational muscle gradually.
We've covered the technical readiness, the accelerating economic model, and the phased adoption strategy. Now we turn to the most critical part for executive decision makers: what food manufacturers need to do now.
Because the core reality is that technology alone is insufficient. Successful deployment requires significant non-technical readiness across process, people, and underlying infrastructure.
Let's start with process readiness and optimization. We must be clear, process optimization should precede or at least strictly accompany robot deployment. The fundamental mantra we advise clients on is that automation magnifies existing process weaknesses.
We saw this cautionary tale during the Tesla Model 3 ramp, where excessive automation layered onto unstable processes resulted in a factory struggling at higher speed. The robot will execute a flawed process faster and more consistently than any human, multiplying the waste exponentially.
So in Wave 1, readiness means rigorously auditing key processes. Ensure ingredient supply is consistent, refine line timing, and establish crystal clear KPIs for the new human-robot processes.
We need to assign process owners for this new operational paradigm and create definitive protocols for handling exceptions. Furthermore, documentation and SOPs must evolve beyond static manuals to dynamic, practical formats like short videos, keeping them current as a robot's task repertoire expands.
In Wave 2 scaling, process harmonization is key. If Line A uses a different procedure for equipment changeover than Line B, scaling robots factory-wide forces a positive unification of best practices.
And this also requires establishing governance structures, specifically an operations control center that tracks robotic cell KPIs in real time. Process engineers can then continuously apply Kaizen principles, continuous improvement, not just to the human activity, but to the automated process.
Then by wave 3, the focus shifts to deep optimization and robustness. This requires rigorous quality control process validation, ensuring the automated systems catch defects as well as or better than humans did, and robust maintenance processes.
You have to integrate the maintenance needs of these new assets into the routine. That means scheduling brief, dedicated downtime for robot preventive maintenance, factoring your workers' service needs into the manufacturing routine.
Next is people readiness, workforce, culture, and governance. Humanoids are highly visible. They physically occupy and take over roles. If this transition is managed poorly, you face severe social risk.
Trust failure, the loss of key tacit knowledge, especially in areas like complex sanitation and daily operating friction. Leadership has to treat this transition as a matter of strict governance, not mere messaging.
The compact leadership establishes must be consistent and shared openly. Routine roles will inevitably shrink, but it will not happen overnight. People will get notice, time, and real options. And crucially, there should be no surprise layoffs tied directly to robotics deployment.
We need to shift from planning and headcount to strategically planning and roles, classifying them as grow, change, shrink, unclear, and sharing that timeline publicly to reduce anxiety and speculation.
This requires defining real pathways in governance. When roles shrink, workers need three practical options: training into technical or supervisory roles, moving to another function or site, or a supported exit package.
And timing is absolutely essential. Early notice prevents your best people, those who hold critical tacit knowledge of sanitation and complex process interactions, from leaving first due to uncertainty. Losing that tacit knowledge can critically impair Wave 2 adoption.
To build legitimacy, we strongly recommend establishing a robotics guild. This is a joint body, including floor representatives and engineers, with real authority to approve automation tasks and resolve issues before they escalate into conflicts.
And this is where the rubber meets the road. If the guild has real authority, what happens when a robot program is technically perfect, but the floor representatives veto it because they believe it creates an unsafe ergonomic situation for the human supervisor?
That tension is exactly what the guild is designed to manage. It moves the conflict from the factory floor, where it causes line stoppage, to a governance forum where decisions are legitimized by joint participation. It ensures safety and operational insight are prioritized over pure theoretical efficiency.
Looking at the waves, Wave 1, pilot, focuses on publishing that clear compact, ensuring safe interaction training for the few employees working alongside the robots, and forming the Robotics Guild.
In Wave 2, scale up, the social risk is highest. You have to scale those pathways, train the workforce for supervision and troubleshooting, and prioritize the retention of critical tacit knowledge, especially in complex sanitation and process control.
Then Wave 3, advanced, becomes governance heavy. You have to maintain credibility through clear communication, build redundancy in those new critical skills, and ensure governance protects safety and quality as autonomy increases exponentially. In union plants, the guild should be formally integrated into joint labor management structures.
Finally, let's address technological readiness and infrastructure. Humanoids require a reliable technology backbone, dependable connectivity, clean data flows, system integration, and strong safety controls. This is the nervous system of the autonomous factory.
Wave 1 requires a simple, isolated setup. Basic monitoring linked into the pilot area's existing network and safety controls. But Wave 2 scaling demands far more extensive preparation. Reliable site-wide connectivity, whether it's high-density Wi-Fi or 5G, is non-negotiable for fleet learning and centralized management.
You need clean, standardized integration links into core systems like manufacturing execution systems, MES, ERP, and computerized maintenance management systems, CMS, along with fleet management tools for oversight across multiple shifts.
And Wave 3 requires deep real-time coordination. Robots, production equipment, and planning systems must work from the same data and rules. This means strong safety and security controls that can handle real-time schedule changes, execute quality holds consistently based on unified data, and ensure that the plant operates reliably with minimal human intervention.
Data fidelity is not just a nice-to-have. It is the key to making autonomy safe, accountable, and scalable.
So to summarize our deep dive, humanoid robots represent a structural, necessary transition in food manufacturing. They offered a pathway from a fragile, labor-dependent operational model to one defined by asset-based resilience and predictable capacity.
The economics are compelling and rapidly accelerating due to external capital flows and AI-driven development. Paybacks are potentially achievable in 9 to 12 months in the mature phase, driven by the labor multiplier, which sees one unit displacing up to 2.2 human equivalents.
This is no longer speculative R&D. It is justifiable capacity insurance against an irreversible labor crisis.
The risk now is not technological failure. It lies entirely in organizational inaction. Waiting for perfect hardware is a flawed strategy because the current bottlenecks are operational process standardization and digital observability.
Early deployment is a finance learning curve that builds the organizational muscles needed for the next wave of capability.
The final provocation we offer is this. Your competitor isn't just buying a robot. They are buying the organizational discipline required to run 80% OEE. Are you ready to pay the price of admission, which is fixing your messy, inconsistent processes and building your technological backbone today before the advanced hardware even arrives?
Thank you for listening to Value Chain Insight Conversations. To deep dive, please see the show notes. For more on food industry topics, visit valuegeneconsulting.com or subscribe wherever you get your podcasts. If today's discussion resonated with you, please do not hesitate to reach out to us to continue this dialogue.